Hi class, thanks for joining me. This is Mr. Stroup. This is going to be our first set of notes for Chapter 12. Chapter 12 is all about gases, and we are going to start out with a bit about what pressure is and the relationship between pressure and volume. A bit about note-taking. Please do take notes. That's going to be important for learning this material. Now, there are two ways to do this. You can either print out the PDF of the standard notes. Those are the fill-in-the-blank notes like we've been using all along. That's available on the website. Or you can just take notes the old-fashioned way. In other words, get yourself some loose leaf paper or, best of all, your chemistry notebook and take notes as we go along. And since this is a movie, if you want to, you can pause it at any time to get caught up and to finish taking notes on that slide. So Chapter 12.1, our aim is to learn about atmospheric pressure and how barometers work, and to learn various units of pressure. So what is pressure? Pressure is a measurement of force over area. In other words, squeezing spread out over a surface. For example, we're all under pressure all the time because of the atmosphere. The air around us is squeezing us. We don't notice it. If you go diving underwater, the pressure goes up by about double every 10 meters, and you start to notice it a lot. So pressure is force spread out over area. Right now, all of the air above you is exerting a pressure on you. There's about 100,000 feet of air between you and space. A 1-inch square column of air that high weighs about 14.7 pounds. So atmospheric pressure is 14.7 pounds per square inch. And you don't just feel that on the top of your head, you feel it all the time, all over your whole body. That's how pressure works. It spreads out and squeezes everywhere. We're just used to that. So pressure is force divided by area. We take the amount of force which is being applied, and we divide that by the amount of area that it's spread out over. And that's our units for force. For example, pounds per square inch is one of the most common units you'll hear. That's how we measure the pressure in things like tires, for example. We got a couple of other ways of measuring pressure, especially when we're trying to find, for example, air pressure, atmospheric pressure. Barometers are one of the most common ways of measuring it. The way a barometer works is you have an upside-down column with a vacuum space on top in some kind of a fluid. Originally, these were set up using water. There's one at Portland State University that uses oil that's even lighter than water, and it's many stories high. But mercury is used very commonly because mercury is so dense, so we can make the whole thing less than a meter high. Atmospheric pressure presses down on the surface of the mercury, and that forces the mercury up into that vacuum-filled column. But it can't go all the way to the top. Its own weight is pulling it down. So the height of the column of mercury that gets pressed up in the barometer gives us a measurement of how strong air pressure is. Earth's atmospheric pressure is strong enough to push that column up about 750 millimeters. So one description we use, or one measurement we use for Earth's atmospheric pressure is we say it is 755, or it's about 760 millimeters of mercury. That changes a little bit day to day with the weather. Air pressure goes up, the column of mercury goes up. Air pressure drops, it goes down. When the mercury is falling, people say, when air pressure is dropping, that usually means there's a storm approaching. Another way of measuring it is a device called a manometer. That measures the pressure of gases in a closed system, comparing it to atmospheric pressure. You can see in that illustration there, we've got a closed tank of gas. If the pressure in that closed tank is more than atmospheric pressure, it'll push that column of that bit of mercury there up higher up on the right-hand side than it is on the left-hand side. If it's lower, then air pressure is stronger, and it's going to press that column of mercury up higher on the left-hand side than the right-hand side. So it's basically comparing pressure in the tank to atmospheric pressure, and the pressure in the tank, the pressure of the gas, is equal to atmospheric pressure plus, really plus or minus, the pressure calculated from the height difference between the right-hand side and the left-hand side. How far up the air pressure in the tank pushes that bit of mercury. We've got a couple of units to measure pressure. 1 atmosphere, the amount of pressure we are feeling right now, is equal to 760 torr, or 760 millimeters of mercury. So a torr is just another word for a millimeter of mercury. We have another measurement for that. We say it is 101,325, about 101,000 pascals. And a pascal is a Newton per square meter. So 1 Newton of force divided by or spread out over 1 square meter is 1 pascal. And we also say 14.69, about 14.7 psi, pounds per square inch. So 14.69 pounds of force or weight spread out over 1 square inch. The SI unit, the standard international unit, the metric system unit, is pascals, 101,325 pascals. Take a minute to write these down. Pause the movie if you need to. So one of the simple things we can do is convert from one unit to another. So let's convert 28 pounds per square I to atmosphere, torr, and pascals. First of all, 28 psi to atmospheres. Well, 1 atmosphere is 14.69 psi. So set it up as a conversion factor. The thing you are converting from is on the bottom, so the unit psi will cancel out. It works out to 28 psi divided by 14.69 psi per atmosphere, and that's just about 1.901, a little less than 2 atmospheres. We can also convert it to torr. So 14.69 psi is 760 torr. That's a conversion factor. The thing we're converting from is on the bottom. So it's 28 times 760 divided by 14.69 gives us 1,448.6 torr. Pause it here for a minute and try the last one. Remember, at 1 atmosphere, 14.69 psi is just about 101,000 pascals. So convert 28 psi to pascals. Pause it, then restart. Okay, 28 psi times the conversion factor, 101,325 pascals over 14.69 psi, 193,131 pascals. Aim 12.2, to understand the law that relates the pressure and volume of a gas and to do calculations with this law. Boyle's law relates pressure and volume. Here's the deal. Pressure is caused by particles, like air molecules, hitting the walls of the container they're in. Air, everything else really, is made up of molecules, small particles. Air is made up of small particles that are always whizzing around through space, and when they hit the walls of whatever their container they're in, they bounce off, and they transfer some of their momentum, some of their kinetic energy to whatever they are bouncing off of. So pressure is caused by all those air molecules bouncing off of the walls of whatever container you've got them stuck in. If you keep the same number of particles but make the space smaller, they'll be hitting the walls more often, so that means there's going to be more pressure. So Boyle's law says when volume decreases, like put the squeeze on that cylinder, pressure increases. Put it another way, at constant temperature, volume and pressure are inversely proportional. So for these purposes, discussing just Boyle's law now, we're saying we're keeping the temperature the same and we're not adding any more gas to the container, or we're not taking any gas away. All we're doing is changing one of these two things, volume or pressure, and seeing what happens to the other one. So we got pressure and volume, and if pressure goes up, then volume has to go down. Pressure and volume, and if pressure goes down, volume has to go up. The two of them are inversely proportional. One goes down, the other goes up. Another way to write that is to say that pressure times volume equals a constant. It always stays the same. One goes up, the other goes down. The two of them multiplied by each other stay constant. So if that's true, then pressure times volume equals a constant. So that's going to be the same as pressure times volume afterwards, after you change one of those two things. So another way to write that is starting pressure times starting volume equals final pressure times final volume. We're using the subscripts here. So subscript 1 is the starting pressure and volume. We change one of those things, and we're going to have subscript 2, a pressure and a volume after the change. Consider a 1.5 liter sample of CCl2F2, that's a nasty gas that people used to use in refrigerators, at 56 torr. If the pressure is changed to 150 torr, what'll happen? Or what must have happened? Remember, we're not adding or taking away any gas. We're not heating it up or cooling it down. The only thing that is changing is the pressure and the volume. So will the volume increase or decrease if we change the pressure from 56 torr to 150 torr? It's going to decrease. The two of them are inversely proportional. If one goes up, the other one has to go down. So same problem, what is the new volume? Okay. First, let's set up a table of everything we know and what we're trying to find out. Pressure 1, volume 1, pressure 2, and volume 2. Pressure 1, that's the pressure before, 56 torr. Volume 1, that's the volume before. We go up to the paragraph at top there, that's a given, 1.5 liters. Pressure 2, this is a given. We said we're changing it to 150 torr. Volume 2 is what we're trying to find. So let's write it out. Pressure 1 times volume 1 equals pressure 2 times volume 2. Pressure times volume stays the same. Pressure times volume before equals pressure times volume after. All right, now you got yourself a basic algebra 1-2 problem. We're solving for V2. That's our unknown. So divide both sides by P2. P2 cancels out on the right. Volume 2 equals pressure 1 times volume 1 over pressure 2. So that's starting pressure, 56 torr, times 1.5 liter, starting volume, divided by final volume, 150 torr, 0.56 liters is our final volume. You can pause the slide, pause the show right here if you need to. Then we're going to try another one. An engine has a volume of 0.725 liters. After the piston moves, the volume is 0.075 liters. The fuel-air mixture is initially at a pressure of 1 atmosphere. What is the compressed pressure? Let's make a table. Pressure 1, volume 1, pressure 2, volume 2. 1 atmosphere before, the volume was 0.725 liters before. The volume after is 0.075 liters. We're trying to find the pressure. Pause the movie here, take a minute, and try this one yourself. Okay, we solved the algebra 1-2 problem. Divide both sides by volume 2 this time. Pressure 2 is pressure 1 times volume 1 divided by volume 2. 1 atmosphere times 0.725 liters divided by 0.075 liters. We've made the volume about 1/10 what it was before. So the pressure goes up to about 10 times what it was before, 9.67 atmospheres. Okay, that's our last slide. We've completed chapter 12.1 through 12.2. I strongly recommend you try the homework problems. That's in the PDF packet that you can download from the website. Next up, we'll do 12.3 and 12.4, then 12.5, 12.6. Then around that time, we're going to do our virtual Charles Law Lab using an online simulator. We'll finish the notes, have a review, and then we will take the test on this unit. Thank you very much for joining me.